How you doing? I'm Mr. Rose, and you can see in front of us that we're going to be looking at one of these questions, and these questions come directly from our textbook that is Young and Freeman, 13th edition, and we are looking at question 22.2. Yes, 22.2, and it's a two-dotter, so it looks like it's kind of difficult, but it's actually not that bad. Write the question down, write the pertinent information, and we'll get right to it. All right, so you see here I've drawn my version of the picture from question 22.2. They told us that we had an electric field of 75 newtons per coulomb coming through this sheet. And this sheet is a flat sheet. It has dimensions of 0.4 meters by 0.6 meters. And this electric field is coming at you at 20 degrees. Now, this is really why it's a two-dot problem, is that 20 degrees. And it's not going to be that difficult, trust me. So what are we trying to find? The question was, find the flux that is going through this sheet. So we can do that. That should be pretty simple. How do we find the flux? Well, things that we should know. We should remember that flux is equal to the surface integral of E dot dA. Everything is my vector. And we know that is going to equal essentially E times A times cosine of theta. So we're going to explore that in a little bit of depth. A is easy. This is a nice little rectangle. So I know A is simply length times width, so that's not going to be super hard. 0.4 times 0.6 is something like 0.24 meters squared. So you may want to jump right into it. Hey, this is easy. This is 75 times 0.224 meters squared times the cosine of 20 degrees. And therein lies the two-dot problem. It's not cosine of 20 degrees. You might be thinking to yourself, why isn't it cosine of 20 degrees? And we have to remind you, what exactly is dA? Remember, dA is perpendicular to the surface and is a vector quantity that happens to have the magnitude of area, A. So dA is perpendicular to the surface. So in essence, we're not looking for this 20 degrees. We're looking for theta as the angle between the normal and my electric field. And again, let's go back and review that. If this electric field is going straight through, say straight up through like so, that would be parallel to my dA, which would be a maximum. My electric field is coming across that way, electric field. That could be perpendicular to dA, and we'd be at a minimum. So my flux, closed surface integral of E dot dA, which is going to be EA cosine theta, where theta is not 20 degrees, but theta is going to be 70 degrees. So I would have my flux equal to 75.0 newtons per coulomb times my 0.24 meters squared times the cosine of 70 degrees. And I grab my calculator. I'd make sure I'm in degrees, and I would get the flux equal to 6.16, I'm going to call it, and I'm going to be in Newton meter squared per coulomb. Nice and simple two-dot problem. Slap it right in the face. That's all I have for you on this question. Look at that. That is less than 5 minutes. Please feel free to like, comment, or subscribe, and you shall see me next time.